Hello, Mr. Allred here again. We've talked a lot about Riemann sums and that they mean the area under a curve. And we've talked about the integral, definite and indefinite, meaning the area under a curve or theoretically the opposite of a derivative. But we've yet to actually really do the process of finding an integral or integration. And it's a really difficult process in general, but luckily we will handle some very simple ones here. And I referred to integration or the integral as the opposite of taking a derivative or the antiderivative. Told you we probably really don't want to call it that all the time, but getting you used to it kind of helps you. So right here in the screen you can see the derivative of x to the n is n times x to the n minus 1, which is the power rule for taking the derivative. That should look very familiar to you. So x to the fifth, if we took the derivative, remember the 5 comes out front, we'd have 5 times x to the, we'd reduce the power, fourth. Okay, 5x to the fourth. So when I say integration, antiderivative, we're going to do that process backwards. Okay. So let's see here. Here are the rules I really want to focus on. And really in this little section we're just going to have one rule and we'll kind of expand upon it and add some other rules to it. But we're going to have a power rule of integration, or you might call it the reverse power rule. So if we want to undo that, we're starting with a function. So we're starting with something, maybe we're starting with x to the fifth. So we want to undo where that would have came from. So remember that when we took the derivative, we multiplied by power and then decreased that power. Let's reverse that process. So instead of decreasing the power, let's increase the power. So here, if we're taking the integral or the antiderivative, we would increase x to the fifth to x to the sixth. So we'll increase it by 1. And it doesn't matter what the exponent is. If it's negative, if it's a fraction, a decimal, irrational, might have a square root there, it increases by 1. Okay? And then if we're reversing that two-step process, after we increased it, instead of multiplying by the exponent, we'll divide by it. So x to the fifth, when we integrate it, becomes x to the sixth divided by 6. And I touched on that since we're reversing this process and we may not know where the function came from exactly, we'll throw some constant out here, just plus c, meaning there could be any number there. In some cases we may narrow that down to an exact number later, and in some cases it'll just stay there. But if you have an indefinite integral with no endpoints, you'll always have a plus c out here, unless you're given some condition. Okay. So that is the main rule we'll be using. Okay. All the examples below, we're going to be using that, and we'll see many different forms of it. Increase the power, divide by the new power. Okay. So to make it a little bit more exciting, we've got two rules down here. One, if we had two functions added or subtracted together, we could do them separately. So we had a sum difference rule for derivatives. We have one for integration. So if we had an x to the fifth plus an x squared, we could do them separately. Also, if we had a coefficient or a multiplier in front of our function, just like when we take the derivative, it stays there. When we take the antiderivative, it stays there as well. Okay, and we'll see some examples of that. So I got plenty of examples down here, I think, but we're not going to do every single one of them. But I will go through a couple of them. Okay. So here, number 17, we're going to integrate x plus 1. So this is two things added together so I can do them separately. So I'm going to reverse the power rule on x. So right now it's x to the first, so it'll be x squared when I increase it by 1, and I'll divide by that new exponent, so x squared over 2. Okay. Then the other part of the sum, 1, That's really just 1x to the 0, so you can increase the power. Or you may remember that if you took the derivative of like 5x, the x went away and you just got the constant. So we're just picking up an x there, 1x, and then plus c. So we used a sum difference rule and the power rule. The one below it here, 3t squared plus t over 2. Okay. Once again, we can separate this into two parts. We'll increase the exponent and make it t cubed. And when we divide by the 3, it'll be 3 over 3, and that coefficient will reduce to 1. This is really 1/2 t squared. Excuse me, 1/2 t. So when you increase that, you get t squared. And if you divide by 2, you get 1/4. So t squared over 4, again, the plus c. So let me go down here to 23. So in 23, we got 1 over x squared and some other stuff. But you remember that when we took derivatives, we didn't like our exponents in the bottom. We would go for negative exponents or fractional exponents long before we would go for fractions or roots. So we're going to rewrite that before we ever do anything. We'll bring it up as x to the negative 2. So that entire function right now, before we integrate, we just rewrote it, is x to the negative 2 minus x squared minus 1/3. So we're going to increase the power. Okay, so starting with the x to the negative 2, if we add 1 to negative 2, it becomes negative 1. So remember, our negative exponents, we have to be very careful with them. Think about it. And then we'll divide by the negative 1. So basically we get negative x to the negative 1. And you can rewrite that back without a negative exponent if you want, but you don't have to. X squared, increase it by 1 is x cubed. Divide by the new exponent of 3, so it'll be over 3. And then the 1/3 picks up an x, and then plus c. Okay, let me find another one here. Let's look at 27. Okay, 27, we have two roots. We have the integral of square root of x, which remember we don't like square roots, we like exponents. So before we do any of the rules, we use an exponent rule to change square root of x to x to the 1/2. Now we haven't done anything except rewrite it. And then cube root of x, we can change that x to the 1/3. So then both of those, we're going to increase the exponent by 1 and divide by the new exponent. So x to the 1/2 becomes x to the 3/2 divided by 3/2. X to the 1/3 becomes x to the 4/3 divided by 4/3. Don't forget the plus c. And it's not too hard to clean that up because if you divide by a fraction, you can flip it over. So 2/3 x to the 3/2 plus 3/4 x to the 4/3 plus c. But there's some other examples here. Just take your time going through them. Make sure that you follow them and understand them, and let me know if you don't. Then I want to do a couple examples here with definite integrals. So we saw how to do the integration. I'm sorry this doesn't show up very good. But we're trying to integrate 9 minus x squared. And now we've got endpoints, negative 1 to 2. So we're going to use the inverse power or the reverse power rule. Integrating 9, we get 9x. Integrating x squared, we get x cubed over 3. And then the common notation is once you have that indefinite integral, that now you'll move the endpoints to the right-hand side of this just to keep track of them. But if you go back a couple of videos when we had a definite integral, we said that after we found the integrated function, we plugged in these endpoints. So we're going to take this statement we've got, 9x minus x cubed over 3, we're going to plug in the 2. So we're going to plug in 2 everywhere we have x, and that gives me 46/3. Okay. And then I'm going to subtract off because basically I'm trying to find the area under this curve, whatever it might look like, between x being negative 1 and x being 2. So between these two endpoints, I'm trying to find the area. So I've got one number here. I'm going to plug in the negative 1 to the same place, and I get negative 26/3. Now if I subtract the negative, it ends up adding it. So if I do the calculations here, I get 24. So if you're having trouble figuring out where that comes from, let me know. One more example here. Might as well let this be the last one. But we're going to go from 1 to 0. So we're under a curve, under the curve x to the 4th minus 3 times the square root of x. We could graph that out and see what it looks like. But we're under that curve, and we're trying to figure out if we run from 1 to 0 or 0 to 1, what the area would be under there. So we could go back and we could draw our curve. We could break it up into many different rectangles, add them all together, make more rectangles, use left side, right side, midpoints, whatever. But we'd always be getting an estimate. So this integration process is going to be exact. But anyway, if I integrate x to the 4th, I get 1/5 x to the 5th. I'll rewrite the square root of x as x to the 1/2. So when I increase that and multiply it by 3 over here, I've got 3x to the 3/2 over 3/2. I can clean that up. Please do. Those 3's cancel out. The 2 ends up on top. But anyway, if you clean that up, you've got to plug in the 1. And if you plug in the 1, it looks like you get 1/5. Then you plug in the 0, and you get 2. Excuse me, no. If you plug in the 1, you get 1/5 minus 2. I apologize. And then when you plug in the 0, you get 0. So the 0 didn't cause any problems there or cause any changes. But if you do all that, you'll get negative 9/5 minus 0. Basically, this is area that is, I believe, below the x-axis. So kind of shows it up as a negative depending on where it is, and we'll talk about that at a later point. But you can calculate the definite integral. It definitely has a connotation to the area under a curve, but it also has some other significant meanings that we could look at later. Okay, look at some of the other examples I've got, and let me know if you have any questions. This is actually easier than all the theory that comes before it, but if you can understand the theory and the painful videos before, it makes a whole lot more sense when you start trying to do applications later on. So hopefully you can do the processes of integration and plugging everything in without too much trouble. Once you get a little practice, it may be a little sketchy of how to get from one place to the other, but hopefully it comes together. Thank you.